Thanks a lot for the kind introduction, Dinaka, and welcome everybody to this new release webinar for our latest version of the Xpress Solver 9.2, which comes with a lot of cool new features I'll talk about in a minute. I start off with my typical slides that the regulars amongst you might have seen a couple of times now, introducing FICO Xpress optimization. So FICO Xpress optimization is a software stack with various different components that covers all different aspects of optimization technology. So there are dedicated solutions which are prepared by our consultants for specific users. You do have the Xpress Workbench, which is our IDE for developing your own optimization models, services, and solution with, well, all the typical cool stuff you get in an IDE, syntax, highlighting, auto-completion, some specific buttons and functionality targeted towards optimization, debugging functionality, and so on. Then you have our Xpress Insight, which is our cloud deployment tool where you can visualize your results, you can quickly share them with your colleagues via the cloud, you can collaborate, deploy apps from there, and so on. The model or the apps in that Xpress Insight cloud environments are typically written in either our own modeling languages, Moselle, or in Python. Next to this, we do have APIs to all the major modeling languages, C++, C#, Java, R, Python, you name it. And then, well, here at the bottom of this, deep in the inside, there sits the Xpress Solver, which is where I work, the heart of the optimization engine, which implements all the fun mathematical technology to solve those problems. And in our solver teams, we do have three major objectives that we go after with each and every release. This is, first of all, performance. So we want to make all our optimization algorithms, which cover really a huge breadth of different paradigms for optimization. We want to make them faster and faster with every release. We want to offer you as our clients new features with every release, new customizability features, maybe new optimization algorithms like this time. And of course, we also always pay high attention on robustness. When the solver is very deterministic, we have a lot of features for numeric stability and so on. And kind of in the realm of this, we also have some news from working with Infeasible problems this time. Okay, so this is the agenda for the next round about 40 minutes. I would first like to speak just a little bit about our new Xpress Global Solver. There will be a dedicated webinar for this next week. Then most time I will probably spend on the MIP solver improvements, where there's some really nice technologies to make this, well, most important, I dare to say, of our solvers faster and ever faster. We also got some really nice improvements for quadratic programming. And as already teased, our detection of irreducible, infeasible subsets got an overhaul. There's much more customizability, much more interactivity for the user now. Performance results is what people are often keen on in these presentations, and some announcements for the end. Okay, so let's get it going with Xpress Global. So this is the name, the term for our new global solver for nonlinear problems. And why do we want to solve nonlinear problems in the first place? Well, obviously, there are many applications which are inherently nonlinear. These may be chemical processing, electrical engineering, gas transmission, portfolio optimization, and so on. And all of these things, just the natural laws of this are nonlinear, like the physics of the gas, for example. And well, you can try to somehow approximate this roughly, and sometimes this works well. In many cases, it doesn't really. So there's a need for some proper nonlinear optimization tools, in which actually inside, again, linearizations are used, but in a very dynamic and adaptive way, such that you can get provable guarantees out of this. Okay, so a bit more formal for the mathematicians. What we are looking at here are problems that can be formulated like this. You minimize an objective function f of x subject to some constraints, g, j of x less than or equal than 0, or you can also have equations, of course, and some, not necessarily all of the variables are supposed to take integer variables. And those functions, they should be analytical. You should be able to just write them down in a closed form, and you have some mild assumptions on how nicely behaved they should be. In math terms, they should be Lipschitz and factorable, but pretty much every function that you ever saw in school, these qualifications apply to them. So for the solvability of such problems, there's an important difference. So for the case that all of the f and g are convex, this is easier. So at least the continuous relaxation. So if you leave out the integralities for a moment, this is solvable fast in a mathematical term for fast. And this is mainly because local optimality implies global optimality in such a case. If at least one of the f or j is non-convex, so it bends in either direction, then this becomes much more complicated already from a theoretical perspective, and this also carries down to computational applications. And in this case, you can have, even for the continuous part, suboptimal local optima or infeasibilities even. I think we see a better slide of this on the next page, where we would like to differentiate the two different offers for nonlinear problems that we now have at Xpress already. Because for more than 10 years already, we already had a nonlinear local solver. So that solver would find you a local minimum. So assume you have a problem defined by two sine curves here that intersect. So everything that's dark blue is the feasible region. This is your even linear objective function here that you want to make as small as possible. So Xpress nonlinear could give you something like this here, a local optimum. So in the closed surroundings, you can't improve the objective, but on the global scale, you actually can, because the global optimum sits over here. So this has been there for many years now. The new thing that we have is our global solver that's guaranteed to give you a globally optimal solution. Forgot to say that nonlinear could already be enhanced with tricks like multi-starts, where you would try to search for different local optima and then get the best of those. But Xpress Global now always will find you a proven global optimum. So it will terminate with this point and provide you proof that you can't do better than this. And well, the beta phase is finished. The full version is now available as part of the 9.2 release. And this is not only for continuous nonlinear problems like the two sine curves here. So if you add integrality on top, you would still find the global optimum now over the integers. In this case, this would be this green solution here in the middle. Okay, and I said something about Lipschitzness. So you wonder what kind of nonlinearities does Xpress Global now support? Well, pretty much everything that you can probably think of. So all combinations of the standard arithmetic operations, so multiplication, division, all different trigonometric functions, sine, cosine, tangent, and their reverse functions, exponentials, logarithms, roots, and potencies. Something that we would call general constraints like absolute value, max, minimum over some terms, piecewise linear and so forth, and all combinations of those. So all of these here are examples of nonlinearities that you could plug into Express globals. There's one important exception. Express nonlinear, the local solver, supports so-called user functions, so black box optimization, where you don't give the function in a closed analytical form, but you implement an oracle that determines whether a given point is feasible or not. Maybe if you're nice, you give it a gradient. So this is still possible in Express nonlinear, but not for global optimization. And much more on this on Express Global, the exact technology, how we solve such problems, the latest developments, and some examples of how you could use this will be given in the webinar next week at the same time, but in a different Zoom room. So you need to register separately for this one. The link from this week won't work here. Okay, so far for Express Global. Let's continue with the MIP improvements. And I slowly traverse from global technology over to MIP, because we start with RLT cuts. So this is a technology that comes from non-convex nonlinear optimization over quadratics. This is an essential technology for cutting there. So assume you have a bilinear relation in there. So you have quadratic, which consists of one variable and another variable, and an auxiliary variable which represents this product. So while xi times xj equals wij. And assume that this is violated. The first thing that you can do is you add these underestimators here. So the blue surface here would be a representation of your product relation, and the yellow plane here is a linear underestimator of this at tight as possible within these given bounds. There's also one on the other side. It might still be that there's a point sitting in the middle which is feasible for those linear underestimators, but violates the product relationship. So in this case, you might still be able to generate a cut from that, a violated linear inequality. This could be done by multiplying some linear constraint, so some other constraint that you've got in your problem that features at least one of the variables in your violated bilinear product by the other variable in here. So you see that if this is a valid constraint, then also this one is, because you just multiply it by a non-negative number. And then you can, exchange your product relations. So you plug in your auxiliary variables for these now created bilinear products here. So this is then still a valid inequality. And this might now be violated if the original product relation was violated. So essentially, this violation carries over here. But as you might see, this is now a linear inequality and can therefore be added as a cut to your LP relaxation. We maybe just look at an example for this. So consider you have a solution for these set of three inequalities. So two of these bilinear terms, and this is the linear constraints. So if you plug in the solution here, you will find that this first one, this bilinear relation, is violated. The other is satisfied, and also the linear constraint is satisfied. Still, we will be able to generate a cut from this here. Even so, these so-called McCormick inequalities, for which or in this case, overestimate this bilinear relationship here, are satisfied. So we see here, I try to visualize this. So the red surface that we see here is v equal to x times y, and this point projected to the vxy space would be, outside the surface. In particular, it would be above and not below, as this inequality asks us to be. And the McCormick estimators would look like this. So here the point A would be exactly on that linear overestimator of your saddle here. And below the other one, so below, because you have some slack here. So this point is kind of in the middle of this, in the inside of this wedge. And what you can now do is that you get an RT cut from the third constraint here. If you multiply this with X, with Y, you would get linear inequality that's still satisfied and tight. You just multiply it with a non-negative number. And then you linearize the reformulating constraints by exchanging xy for v and zy for w. And this you can simply do by adding these three inequality to each other. So here the x times y will cancel out if you add these two things. The z y will cancel out if you add this on top, and you're left with v w less or equal than 3y. And this linear inequality is violated. It's just inherited the sum of violations from the first and the second bilinear relation here. And this you can now add to your linear relaxation. Okay, so why do I present this technology as an improvement for MIP? It's certainly an improvement for non-convex quadratics, no doubt, but you would also be able to apply this to MIP problems because you can look for implied product relations. So you often have something like this reformulated in a linear fashion if the xi is binary. So there's only two feasible solutions to this bilinear product relation. So this could be reformulated as these two linear constraints. If one of the variable is binary, you can just check that this checks out. So if xi is 0, this forces the first one forces wij to be 0. If xi is 1, then wij becomes less or equal than xj. Okay, because this one gets eliminated here. Okay, so this checks out. This is a valid reformulation for the case that xy is binary. And you can detect such structures here in your MIP formulation and apply the same technology that we just saw by imagining them essentially as bilinear relations between the xi, xj, and wij variable. Okay, so this technology makes our global solver significantly faster, 16% overall, 20% overall on affected models, which is the majority of models here. But a little bit surprisingly, in this extent, almost half of the MIP models also feature some structures to which you can apply RLT cuts. And you still get something like a 2 to 4% improvement on MIP from this cutting technology. Another new feature that we added are our root parallel heuristics. So these are heuristics that run in parallel to the cut loop at the root. This is enabled by default. Actually, already has been before 9.2. There's a control backgrounds, max threads that allows you to determine how many threads you want to dedicate to these so-called background tasks, which currently are only heuristics, but potentially in future this could also be different things. And some specific controls to select particular heuristics that you would like to run by default. The so-called feasibility jump, not feasibility pump, feasibility jump heuristic ones, which we introduced in Xpress 9.0, and our LP-centered local search, which some of you might know from the letter L in the logs. And given that this is depending on how many threads are available for background tasks, also what will be enabled depends on the number of threads. So if you only have very few threads, only feasibility jump will run, and the L heuristic is only added if sufficiently many threads are available. If you were a user of our Hero threads control, you might instead want to try this one now. Speaking of heuristics, there's one new heuristics that we implemented. It's called Shift&Propagate. It's a heuristic that doesn't solve any LP relaxations, but it just tries to set variables to values where it thinks they are kind of good, and then propagates the impact of these variable settings. So this is like several rounds of fixing and propagating and fixing and propagating and so on. And in each single round, you would select one column that's not yet fixed, fix it to a value that minimizes a certain score, which is a combination of the objective value, so you want to go for good solutions, and the row violations that you currently have. So you're all of the time, you can imagine you work with an infeasible integer reference point. Sorry, over here. So you start with some infeasible integer reference point. You check how many rows are violated in each of the 3 dimensions here. You see that the most you can reduce the violations if you push up the first variable here. So you would fix that 1 to 2. Then propagate the effect of these fixings. So one of the constraints would now tell you if this first variable is 2, then both of the other 2 have to be at least 1. This brings you closer to the integer hull. And now you look again for a variable that you can fix to a certain value to reduce the number of row violations. You see that on the second variable, if you push that to 2, there's actually no more violations in that variable, and also not in the last remaining one. You would get a feasible solution now. So this is like 2 rounds of the Shift&Propagate algorithm. Currently, we would only get this in our emphasized heuristic search mode, Euro emphasis equals 2. And there's a new control if you want to give it a shot anyway, where you can manually enable or disable this heuristic. Taking heuristics aside, there's some more improvements that we did, so to say, on the dual side of things. One of them, funnily enough, is called Primal degeneracy reduced cost. So primal degeneracy is a term that comes from the LP world. So the solution of a linear program is called primal degenerate, when you can have several different bases representing the same solution. And this is the case when there are more than the required number of constraints tied at this particular point. So here, so the red one is the objective. We are in 2 dimensions, so we would only need two constraints to define a single point. But we actually got these 2 and 3, 4, 5, 6, 7, I think, different constraints, which are all tied at the single point. So there's many different bases that you could select that would prove the optimality of this point here. So you can detect primal degenerate columns because they are basic, but they at the same time sit at their bound. And this means that you could exchange such a column for a different non-basic column. So just consider this very simple inequality here. So if one of these 2 columns is in the basis and this constraint is tight, you can always exchange it for the other one. So why does this matter? Okay, interesting so far. Because you can use this in reduced cost fixing. So assume this above example here has one of the variables being integer, or in particular binary in that case. And the other one is a continuous variable. This is like very typical indicator or big M constraints, where you would use the binary Y to activate or deactivate a continuous variable X. So if we have our variable y in the non-basis, then we can do reduced cost fixing and exploit the inequality of y. If it's x instead, we cannot do this. So we would prefer a particular one of these two variables to be basic and the other one non-basic. And this can then be exploited by scanning for such primal degenerate integers in our current LP relaxation, and then find an alternative dual solution to get non-zero reduced costs for the integer variables and potentially fix some of them via reduced cost fixing. There are some improvements that we made in branching. So we looked at strong branching, which is a technology that tentatively branches on several branching candidates to evaluate the impact. So it actually creates all of these branches. It actually solves the relaxation in each of these branching, which is quite expensive, but it's a very effective branching strategy. And there's another technology called single dual pivots, which is something like a one-step strong branch, which is for linear algebra reasons much cheaper to compute. So this is something which we would do further down the road usually. But then on, well, now dual, not primal degenerate problems, strong branching is often inferior. So you would do the strong branch, but still in your newly created sub problems, you wouldn't see any progress in the objective value. So to filter this more effectively, we would now do on very degenerate problems always use dual pivots instead of strong branches. So that's one branching improvement, and the other one is that we now got a different rule to mix different statistics of our branching rules, in particular history-based statistics, where one of the most common things are so-called pseudo costs, which tell you the impact on the objective function branching on a certain variable had in the past, and the so-called resets or conflict statistics, which means how often was a variable involved into detecting an infeasibility. And these two were previously mixed in a very hierarchical fashion, and now we got like a combination of these for branching. Well, a detail in the branching rule, but one that gives some nice performance improvements. And there's also been some improvements on cutting, in particular on mixed integer rounding cuts. So on the right-hand side here, I tried to visualize what the general idea of mixed integer rounding is in the first place. So assume you got a problem where you have one integer variable, so that's the x variable here, and one continuous variable. I call it this s here in the example. And so everything that's well, blue plus the thing in the middle here, where I already applied this disjunction, which I will talk about in the middle, is the feasible region of the relaxation. The feasible solution are the black thick stripes. So this is the set of feasible MIP solutions. So even for this trivial problem where you have these two variables and the simplest relation between them, namely an inequality between just those two variables, you might get an optimal solution that's fractional. And there is a way to cut this off by so-called mixed integer rounding. And this applies an disjunctive argument. You find an inequality that is valid only for the upper part here. So if you would branch on that fractionality of x and force x to be greater or equal to, what is this one? Well, 1.5 rounded up, or less or equal to 1.5 rounded down, you find an inequality that's valid for this part, and the same inequality which is valid for this part. And when you know that it's valid for each of the parts alone, then it needs to be valid for the overall problem. And in this particular case, so this is the disjunction, as I said, that you apply, and you can construct this so-called mir cut. Then, which you can check out is just adding 1 times the fractionality of b times the third inequality. So adding these two here gives this linear inequality. And equivalently, you can also do this by using the two bounds of x and s. This is 2 and 4. Adding with a certain factor gives you the same inequality. So this is the so-called meerkat. And the whole argument here, you can extend it to rows with many integers and many continuous variables, which is a bit harder to visualize then, but it's really just the same technology. And you can generate additional rows to cut from, so addition on top of your model constraints by aggregating some of your model constraints. So adding your model constraints to each other gives you a new inequality that's valid for your problem, and then apply mixed integer rounding to this one. And this is where we got our improvements. So we now better handle cascade effects in these aggregations. When you aggregate many sparse rows together, this might potentially lead to a dense row, which is bad. We've got now a better handling of this, and we avoid some full exploration of meerkats and problems with many fractionates, some better criteria to steer this. Okay, so far for the technical part. This is a little overview of the performance improvements, which I mainly added to, well, raise some awareness of the state of the art in MIP solving, namely that all of these typically only provide some tiny improvements, like 1 to 2%. Some of them, well, only tiny improvements overall, but they only apply to a very restricted set of models, like these dual pivots for dual degenerate models, only applies to only 9% of the MIPs in our test set, but on this one, it really, well, it's a very effective technologies, which makes them like something like 20% faster. But overall, taking all of these together, you will still see a significant speed up, as I will show you in a few slides. Before that, I would like to talk about some improvements to our continuous solvers, in particular, quadratic programming solvers. So there's one simple functionality here, which allows you to reformulate an MIQP as an MIQCP. So for instances, mixed integer instances with a quadratic objective, but linear constraints, in some, not in all cases, it can be beneficial to move the objective into a constraint and work with a linear objective. And there's now two controls which allow you that this is done by the solver rather than doing it yourself. And also we improved our quadratic simplex, where here's like a visualization of a quadratic programming problem. So the red lines here indicate the quadratic objective, and this is an underlying linear constraint system. So there's a special simplex algorithm for these kind of problems, where we now would use in the phase one linear simplex and the linear dual simplex to find initial feasible solutions, which is particularly effective when the number of quadratic variables is small. We implemented partial pricing for primal and dual quadratic simplex, and did some other little tricks and features which give some really nice performance improvements on these QP problems. Also, we now have a quadratic crossover for the barrier algorithm. So also for solving QPs via barrier, you now get some new features, and we implemented a warm start for quadratic simplex, not only internally, that's something that we had, but you can now warm start by loading in a solution into the solver, and then warm start from that solution. If you got this, for example, from a previous iteration of your QP solving procedure in your problem solving chain. Okay, let's switch gears and talk about IISs, irreducible infeasible subsets, which got some improvements. And before I talk about these improvements in details, I should probably say what an IIS is exactly. And I'm bold enough to do this with a nonlinear example here. So take this set of 3 nonlinear inequality constraints. So the shaded area in each color should indicate a feasible region of an individual constraint. So like an exponent here, some quadratic function here, and a trigonometric function over here. So you see that this set of 3 inequalities, all 3 together, is infeasible because there's no point that lies inside all 3 of the shaded areas. So this is taking all these 3 together is an infeasible problem. It's also an irreducible infeasible problem because for each combination of these 3, there's always a feasible solution that fulfills 2 of them. So when you take either one of them away, the problem will get feasible. You need all 3 to get infeasibility. So this is what you call an irreducible infeasible subset, a set of constraints that prove infeasibility together, but you can't take any of them away. And of course, these could be part of a much larger set of constraints. Okay, so with that out of the way, there's now a new control called IIS ops to specify which types of constraints, let's say, you want to have in your IIS and which not. Do you only want to see equality constraints? Do you try to find an IIS on equality constraints only? Or do you want to involve fixed variables, or is a fixed variable always a certain given in your problem? Do you want to leave out integer entities or not? Do you want to allow relaxing bounds and so on? So there's a high customizability. There's new logging functionality, which shows you some progress between the undecided and the included constraints. And you would also now get partial results when interrupted prematurely. So until recently, if you did not find an IIS within your time limit, the solver would just stop. Now you get an infeasible subset, which is not necessarily irreducible, and a solution status which tells you which of the situations applies. And as I already spoiled, IIS will also be available for nonlinear problems, which is also new. We didn't offer this previously. Of course, you will need a global solver license for this. And again, just like in all, global user functions are not supported here, but all other kinds of nonlinearities, convex, non-convex, doesn't matter. And you will get this through all APIs. Okay, getting to the part that everyone is looking most forward to in these kind of presentations, the performance numbers. How much faster did Express get in the last year? So this is the typical year-on-year comparison that we look at, comparing the just recently released 9.2 version against the current version a year ago from now, which was 8.14 at this time. And we see that with the improvements on quadratic programming problems, we got a significant speed up on our most important problem type of mixed integer programming problems. We got a 16% speed up overall, and a 25% speed up on models that take more than 100 seconds to solve. This is a pretty solid number, 25% improvement year on year. And while global benchmark to be taken with a grain of salt, so this is comparing against our beta version, which did not have all of the features implemented yet. So it's kind of expected that we see a big speed up here in the very early phase of this project. But yeah, we are confident that we have a very competitive global solver by now with the full release of 9.2. So if you tried the beta, might be a good idea to try the 9.2 version again. Some announcements about API changes. Pay attention if you used any of them, and this might prove useful to you. So our XPRS add calls function and the XPRS load functions now allow for null arguments for the objective, the lower bounds and upper bounds. Also, when using our functions XPRS NLP get formula string and SLP get coefficient string, this can also now be queried to only get the length of the formula string. So you can do this by passing in 0 as the max byte argument, then allocating a string of the corresponding size and calling that function. Again, the version information is now also available fully at compile time via these following constants. And this function, the function Xpress get version numbers, does no longer require Xpress init to be called. So you can do this before initialization, which comes in handy if your application works with different versions of Xpress at the same time. There's some other API and usability changes and improvements. So the tuner now got a method specifically for the global solver where you can tune performance on nonlinear problems. Also, our possibility to tune whole sets of problems now is available via the API. There's some improvements in Python with some new convenience functions, and our R interface now supports nonlinear functions. And well, you will get warnings if you use deprecated functions, attributes, or controls. We also added now warnings for deprecated callbacks. And just be aware that if you receive such a warning, you might expect that the deprecated functionality will be removed 2 years after it has been first deprecated. So don't wait too long with acting on this. Okay, we are coming to the end of our 45 minutes planned presentation times with some announcements. If you are an academic user, then our Xpress Best Paper Award might be of interest to you. So the Xpress Best Paper Award acknowledges outstanding papers in the area of operations research, mathematical optimizations, and related fields. So this is really an award on the scientific quality of published papers, with the one side conditions that it only qualifies for papers that use some Xpress optimization products. It's awarded annually with a nice prize money attached to it. And well, papers have to be published in a peer-reviewed journal, and this is the jury of researchers that's evaluating these. The deadline for the next submission for all papers published in 2022 and 2023 is January next year. So if you're really fast, you might still be able to publish a paper, write a paper, get it published, and submit it by then. And we just announced our first winners. This is Alexander Morera and his team with a nice work on showing how you can use multi-objective robust optimization to plan the energy transition, taking into consideration the effects of the changing climate, like increased chances of certain kinds of natural disasters and so on in South America. So this was a really cool paper, and there's also a great runner-up on port logistics. And I realized now, don't know whether Dina has them available quickly, but I forgot to put the links to our blog posts on these two works, which nicely summarize the applications behind them. Go on our Xpress community, optimization community, and then you under blogs, and you will quickly find these two blogs, which explain what cool research you can do with Xpress. With that, and then thank you for your attention. I'm happy to answer questions, and as I said, check out our optimization community with blogs, documentation, free community, and academic licenses, and much more.